I am Manoj Arora, Professor of Geomatics Engineering in the Department of Civil Engineering, IIT Roorkee. I shall be speaking on hyperspectral image classification algorithms under the IARS Outreach Distance Learning Program for Indian universities. This will be the outline of my lecture. Although you people must have been exposed to hyperspectral imaging, its applications and several other things, I would start with a brief review of that, followed with a brief review on feature reduction, and then we'll focus on classification both per pixel and subpixel, and may throw some light on accuracy assessment. Now, as you know, as we move in 21st century, remote sensing has grown by day to day. Now, for the last 40 years, several advancements have taken place in the area of remote sensing. More satellites based sensors have been launched. As a result, the resolution has increased like anything, whether it is spatial resolution, spectral resolution and temporal resolution. So in terms of spatial resolution, nowadays we are getting information as fine as at a spatial resolution of 40 centimeter. When it comes to spectral resolution, these days we are getting data in more than 100-200 bands at very fine wavelength regions. Similarly, when we combine data from different sensors, temporal resolution has also improved. As a result, we are getting almost data in terabytes on day-to-day basis. So we have indeed excelled in data acquisition capabilities, but when it comes to analysis of that data, to derive information from that data, we have to do a lot. Indeed, several things have happened. We are nowadays talking of even polarimetric scattering, interferometry and so on. So this hyperspectral bands or availability of hyperspectral data has thrown new challenges to the remote sensing community to derive information from that data set. Not only that, the data from other sources can also be integrated with these hyperspectral, microwave or whatever. These data can be utilized to its effect only when my data analysis techniques are good. When we see the information extraction from remote sensing data, we can derive maps, thematic maps like land cover maps, agriculture maps, forest maps, snow cover maps and so on. We can derive some physical parameters like leaf area index, biomass, soil moisture, tree volume and all those things, which definitely require a new generation of techniques. So as I see the remote sensing from a spectral point of view, the spectral resolution has improved from wide broad band panchromatic to multispectral to hyperspectral, and maybe in near future thousands of bands, what we call ultraspectral. So what is hyperspectral imaging? As you all know, when a spectral measurement is performed using hundreds of narrow contiguous bands, the resulting image is known as a hyperspectral image. The hyperspectral has given us an advantage in the sense that we are now getting almost continuous spectra of various classes which we want to map from remote sensing data. For example, soil, water, vegetation. As you can see here, almost continuous spectra we are getting. Why? Because my wavelength interval has become smaller and smaller and almost contiguous. So this basically matches with the spectra which we collect on the ground. So that means it has given us lot of opportunity to really derive several parameters from the remote sensing data. So this is again a kind of reflectance curve, as you may all know, which is a reflectance curve of vegetation, wherein almost continuous spectra you can get from hyperspectral sensor, unlike multispectral, which is kind of discrete spectra I am getting here. I can get continuous spectra. This has really helped us in mapping very fine objects also, which can be spectrally resolved in these data set. So but this would definitely require data from the ground in the form of spectral signature libraries, about which obviously you might have studied in the previous lecture. We require spectral signatures of thousands of materials on the surface of Earth which have been collected as libraries. So spectral libraries are there, and these signatures will be used as known data for deriving information from the satellite based images. So the data from field has an important role to play, and this data will be used as a reference data for deriving information from the satellite data. So in the field, as you all know, the data can be gathered from spectroradiometers which are available at different ranges, right from visible to shortwave infrared, which is the kind of range which is available these days, in which the satellite data is available these days. These are the names of common hyperspectral systems: airborne Everest, CASI, HIDICE and HIMAP. And when I look at satellite based sensors, I think Hyperion, I would say, would come under the family of hyperspectral data, wherein I can get information in hundreds of bands. These are some of the snapshots of an area obtained from different hyperspectral sensors, providing data at different spatial resolution. For example, Hyperion, which is providing me data at 30-meter resolution, but airborne hyperspectral sensors are giving me data at finer spatial resolution up to 1.5 meter also. When I look at the software for hyperspectral data processing, there are some commercial packages in which this hyperspectral image processing modules or tools are available, but still we have to go a long way in development of software for hyperspectral data processing. That's what I was telling right in the beginning, that the advantages of hyperspectral data is in mapping finer detail. For example, in mining and geology, mineral, more accurate remote sensing exploration can be done. In forestry, forest health, infestations, forest productivity, yield analysis, forest inventory become easier. And similarly in agriculture, yield production, commodities of crop health and so on is possible from hyperspectral imaging. So it has got lot of benefits, but these benefits can be served only when the data can be when the information can be extracted accurately from this data. Now when I look at hyperspectral data processing, there are a set of procedures which one has to adopt. For example, pre-processing is the first step, and I gather there have been couple of lectures on only on pre-processing, and which basically requires radiometric corrections, atmospheric corrections and geometric corrections. Similarly, once the data has been corrected for these errors, if there are any, then you pass that data through feature reduction steps. So now what happens when the hyperspectral data are taken in contiguous bands? So some of the bands may be providing me correlated information, so it may be providing me some kind of redundant information which I can bin out by projecting the data in some other dimension space, just to increase the efficiency of the work, and also to use those bands which really carry the information, and the information is really relevant to the application which I am interested in. Then the classification stage is there, which is a kind of mapping stage, I would say. But in classification, I can perform per pixel classification, subpixel classification, and super resolution mapping. I shall be talking on all these three classification scenarios in my further slides. There is another application which is particularly important to army personnel, like anomaly and target detection. If they want to detect small targets from the images, from the hyperspectral images, then a set of algorithms have to be used to detect those anomalies and targets. So I shall be talking about all these things in further slides. So pre-processing, I am sure you have already studied in detail about radiometric corrections, atmospheric corrections, and geometric corrections, and I am assuming that the audience is very well known about these pre-processing methods from your previous lectures. Similarly, feature reduction also, I have found that in feature reduction also some lectures have already been taken. Just to give you a brief recap of what you would have studied earlier, for example, feature reduction can be carried out using feature extraction. Basically, the aim is to reduce the dimensionality in such a way that the original bands are transformed into a new set of coordinates or features. For example, that's what you do in principal component analysis. The other way to reduce the feature, as you know, is feature selection, wherein bands that do not aid in discriminating the classes may be removed. So basically, we are trying to use only those bands from the original set of bands wherein classes can be discriminated clearly. So this is just a kind of mathematical representation of feature selection and feature extraction. So for example, if I have observation vector in the form of x1, x2, xn, these are my bands. So when I apply feature selection, m number of bands would be there as an output. Rest of the bands would be removed, though the output which you are getting here are basically the useful bands for that set of classes. In feature extraction, this is my observed data. I apply a feature extraction technique which can be any kind of transformation, like principal component analysis. When you apply that, you will get a set of components which will be equal to the number of original bands, but then these components are kept in an order, certain order, wherein top few components are the useful ones, which I can say that those are the m components obtained from that original set of n bands, which can be used for further classification. So there are many feature extraction approaches. Principal component analysis is a well-known approach. Then recently, segmented principal component analysis, independent component analysis, projection pursuit, orthogonal subspace projection, and even wavelet based transformation. These are the mathematical tools which have been used to extract features from remote sensing data. So when we say extract feature, it does not mean that we are extracting earth surface feature. It means reducing the dimensionality of data. So it can be done by feature selection also. There also a set of approaches are there, like discriminant analysis, which is a well-known statistical approach. Then divergence analysis, a kind of separability analysis, wherein we are trying to quantify the discrimination between the two classes by way of several measures, for example divergence, transform divergence, Bhattacharya distance, Jeffrey-Matsuda distance, and recently some machine learning tools have also been used to select features from that bunch of hyperspectral data, for example neural network. But when I look at principal component analysis for feature extraction, it indeed requires high computing load when it comes to hyperspectral data. Further, PCA operates on global statistics, and there may be a tendency that it may overlook the local variances that may be helpful for the detection of targets. Now, as you know, why hyperspectral data has come? I really want to detect those small objects, but if I want to use that data, if I want to use all the bands, then there is problem of computational load. So I go for PCA, but PCA loses that information. So what to do? So therefore segmented PCA came, wherein I can use it effectively in such a way that the correlation which is expressed in various bands can be blocked in the form of groups, and then PCA is applied on those groups so that those local variances are also captured. So this is a kind of correlation matrix, a kind of image also, you can say correlation image, which has been obtained from those spectral bands. So as you can see, on this side it is the number of bands, again here on this side also the same number of bands. So when I look at the correlation between this set of band, so this set of band is having one correlation, high correlation. Brighter the display here you see, that means higher is the correlation. Then there is this block which is again high correlation, this block and this block. So in a way along this line I can find that this block is there, this block is there, this block is there, this block is there. So those 200 odd bands can be converted into these blocks of high correlation, and then PCA can be applied on each of these blocks from where the components can be obtained. So this gives you another view of the what I just said. So original bands, you apply some kind of threshold on the correlation to find out subgroups from the original bands, and then apply principal components on these group to identify those many components. For example, here n1 component, n2 components, and so on. From here then you arrange those in descending order of their variance and take the cumulative sum of that. So maybe top 1, 2, 3 components may be good enough in that block. So we take for example 2 components from this block, 2 from this block, 2 from this block, then that forms my database for further classification or information extraction. So this we applied on a experimental data set. It is a very well known data set available at Purdue University website. Most of the people have used these data sets for their research whenever a new algorithm has been developed. So this data set has been used. It is a average image. From original 220 bands we have retained 182 bands, wherein water absorption bands and some bands which were having no data have been removed. It is an agriculture area containing 16 crop classes, and the size of the image is 145 by 145 pixels. So when we applied segmented PCA on this data set, the data set was, so 182 bands were segmented into 6 segments based upon the threshold on the correlation which we applied, and from those segments, based upon the cumulative variance, we selected some components. So in segment 1, 1 component, in segment 2, 2 to 35 components, and so on. So finally we were left with 1, 2, 3 and 3, 6 and 3, 9 components. So those original 220 bands data has now been reduced to 9 components. So those 9 components now can be used for image classification. Now image classification appears to be the most important task in deriving information from those hyperspectral data. It could be all the bands, or it could be the reduced data set which may come via feature extraction or feature selection. Now when I look at the image classification nomenclature, I can see several kinds of classifications are there, but let me divide that in some way. For example, I can have 3 different scenarios. First one, point per pixel hard or crisp classification. That means 1 pixel is allocated to one class. The next scenario, that is second scenario, is subpixel soft or fuzzy classification, wherein the pixel is decomposed into various class proportion. It is a specific problem which is there in coarse spatial resolution data when the pixel may contain many classes. Then there is another scenario wherein I gather information from the neighboring pixel in the form of texture, context, which may lead to spatial classification. That means a group of pixels is allocated to one single class. So this may lead to some kind of object based image classification also at the end of the day. Now these three scenarios, whether it is per pixel, subpixel or object based classification, here I can apply classification in supervised way and unsupervised way, as you might have known earlier, and whether it is a supervised way or unsupervised way, both parametric and non-parametric classification methods can be adopted to perform a supervised or unsupervised classification. So for example, if I say maximum likelihood classifier, what is this? I can very well say that it is a supervised parametric method of classification to perform per pixel or subpixel classification. So basically nowadays we are moving from per pixel to object classification, and this is the kind of image which shows that if the spatial resolution of the data is more, then some of the pixels could be mixed pixels. So I am interested in finding out this proportion of this class and the proportion of this class. So various scenarios are available to me. This way, now let us see what are the various approaches which we can use to perform per pixel classification. So what do? I just have a matrix. This is my basically output, the digital output. So each pixel will be allocated to one of the classes which would be color coded to ultimately get a classified image. So this is what basically I want from a per pixel classification. When I look at subpixel classification, now this is my remote sensing data. Here I will apply subpixel classification. Now here, unlike per pixel classification wherein each pixel is allocated to one of the class, now here each pixel is allocated to a class proportion. So depending upon the number of classes, I am going to get a set of images which will denote the class proportion of a class there. So for example, here this is 70% class 1, which can be taken as vegetation, 10% is say soil, 10% is wetland, and 10% is water. Across this you will get the 100%. So ultimately what I am getting from subpixel classification, I am getting class proportions. So whether I perform per pixel classification or subpixel classification or textural classification, I first need to define the mapping approach. That means I must define the classification scheme, the number of classes which I want to map. This may depend upon the application. Based upon that, I will have to select the proper satellite data, and also I have to look for the reference data which will help me in performing supervised classification and for the accuracy assessment of that particular image. So this is followed with feature extraction and selection, as I told you earlier, and then classification and accuracy assessment. So typically when a supervised image classification is performed, what we do, we identify certain training areas. As you might all know from your previous lecture, training areas are those areas in the image about which I know. That means class identity of pixels within these training areas will be known to me from some reference data. From these training areas, I'll generate some statistics, what we call training data statistics or training data signatures. These signatures will go in the allocation stage, wherein I will apply certain decision rule, for example maximum likelihood decision rule, wherein based upon that statistics each pixel will be allocated to one of the classes to produce a per pixel classification. Now this has to put to accuracy assessment stage, which is also known as testing stage, wherein the quality of this classification is assessed. Now, to perform this classification, as you all know, for multispectral data, these are the standard classifiers like parallelepiped classifier, minimum distance to mean classifier, maximum likelihood classifier. These are very well known classifiers which are available to the user community to produce classification from multispectral data. But there are problems with these parametric classifiers, particularly for hyperspectral dataset. For example, in training stage, there are usual restrictions on size, training sample size, due to cost and other consideration. This may lead to inadequate sampling when it comes to hyperspectral images. In case of parametric, the size of training sample does matter to estimate these parameters. But as the dimensionality increases, as is the case with hyperspectral data, for a fixed sample size, accuracy of the parameter decreases and hence the accuracy of classification. Further, it is common that mixed pixels dominate the image, but only pure pixels are selected for training. So training sample size will always be an issue. So therefore, parametric classifiers have limitations in producing classification, quality classification from hyperspectral data. So are parametric classifiers good? I have some reservations. For example, these depend highly on the statistical distribution assumption, which may not be met by the training data because of want of sufficient number of training pixels. Similarly, these have limitations in processing data at a different measurement scales, and also obviously have limitations in processing hyperspectral data. So what should I do? I should go for non-parametric classifiers which make no assumption about the data distribution, as they use information directly from the training pixels. So parameters are not derived, which are a representative of training data in parametric classifiers. Here we use training data directly in the classification process. Now when I look at the literature, a number of classifiers have been developed which can come under the category of non-parametric classifiers, and these classifiers have come from different theories. Theories of artificial intelligence, theory of information theory, machine learning, fuzzy set based theory, and so on. So some of these approaches are neural network classification, decision trees and expert systems, support vector machines, fuzzy set based methods, evidential reasoning, and many more. And this list is not exhaustive. There are many more. There are specific classifiers which I am going to explain here, and I am going to show you some results from these classifiers, which are spectral correlation mapper, neural network classification, and decision tree classification. So what is a spectral correlation mapper? Here we are trying to find out correlation between the unknown spectra and the reference spectra. So unknown pixel, spectrum of unknown pixel will be related to the reference spectra. So whichever pixel will be close to the reference spectra, the correlation R of that pixel will be high. Now what is R here? R is defined as, it is composed of X, the image spectrum or the DN value of the pixel in all spectral bands. X bar is the mean of the DN values of the same pixel over all spectral bands, and Y is the reference spectrum of a class in all spectral bands, whereas Y bar is the mean of the reference spectra of a class over all spectral bands. So you have on one hand a spectra of the pixel, and on the other hand you have a spectra of the classes. Now the spectra of the classes can be obtained from either laboratory or field, or from a spectral library, as you know, or even from the training data. Now we are basically trying to find out this R value. So the pixel will be allocated to that spectra where the correlation or the R value is the highest. So my aim is to classify pixel x given digital number value of pixel x for every band. Use this correlation to find out R for each pixel and assign the pixel to that class which has got the maximum correlation. When it comes to neural network, a neural network may be considered to comprise of a relatively large number of simple processing units that work in parallel to classify input-output classes. In our context, for example, hyperspectral image, wherein the input data would be digital number values in various spectral bands, or what we call features, if the hyperspectral data has been reduced by any feature extraction technique. The output data obviously would be some kind of thematic classes, for example land use, land cover classes. So this picture explains to you clearly about the process of neural network. Here an artificial neural network is composed of input layer, output layer and a couple of hidden layers. At the input layer there are neurons. These neurons corresponds to the remote sensing variables. In our case the variables are my spectral bands or the features. So number of neurons in the input layer are defined by the number of input data. At the output level, the number of neurons are equal to the number of classes being mapped. So in number of neurons in input layer and output layer are defined by design, whereas the number of neurons in the hidden layers are obtained by trial and error method. So now what is the process? The process is that I first need to train this neural network. Now you can also see that each neuron in one layer is connected to the other neuron in the other layer, next layer. So these connections will carry weight. Now initially when we give data for a pixel here, some weights are assigned randomly on these connections. Then in an iterative process these weights are adjusted during the training phase till the neural network is stabilized. Once that is done, then these weights now become my training data signatures, and if I put any unknown spectra and pass that through these weights, ultimately that will give me some class output. So this explains more clearly here. So these are my 4 bands x1, x2, x3, x4. These are my land cover classes. So when I say 1, 2, 3, 4, 5, so I want to map 5 classes from that data. So for example first pixel may belong to class 1 here, which has to be mapped like this. So first one will be given 1, rest will be given 0. If it is a class 2, then this will be 0, this will be 1, 0, 0, 0, like this. So I'll give some data. That data will be passed through this, and ultimately it will be compared with the target value and an error would be determined. That error would be back propagated here, and then the weights are adjusted again at each connection to finally again modify that value till I am satisfied with that value. This process continues, and once I am satisfied, then the network is assumed to be trained, and the pixel once the network is assumed to be trained, then I will apply an unknown data onto this trained neural network to classify that pixel to one of the classes. But when it comes to neural network classification, I obviously need to set several parameters by trial and error, which is basically number of hidden layers, number of hidden nodes, some other training parameters like initialization of weights, training sample size, learning rate, momentum factor, several things I have to do in a given training algorithm. The algorithm which was just explained to you was backpropagation learning algorithm, and there are several more. Now neural network basically minimizes the error over the training data, which may have limitations when it comes to generalization capabilities. So any unknown data which may not be explained, which may not be explained by the training data, the neural network may uh, may not be giving me kind of general information. So what has come only recently, support vector machines have also come for class, which have been used for classification purposes. These are introduced by Boser and other people, and basically it is not a hardware as the name suggests. It is basically an approach, a mathematical tool coming from machine learning theory, which uses an optimizer to find an optimal hyperplane. So using this optimization procedure, the exemplars that form the boundaries of the classes are identified, which are known as support vectors, as can be seen here. For example, I want to segregate the data into two classes, the green circles and the red circles. So basically I want to find this line in such a way that the pixels occurring at the boundaries, the distance between these is maximized. So those boundary pixels would be known as support vectors. But how to find that optimal hyperplane? That is the problem, because there could be many planes. So I need to find out that plane which is indeed optimal, which can separate out these two classes into two. So this is how I will go about it. So I have to find these support vectors, nearby vectors, which occur at the boundaries of the two classes, which can maximize this distance. But the disadvantage of hyperplane is that if the classes are mixed, then it is very difficult. So you go for non-linear hyperplane. But again, that is also a mathematically complex problem. So what happens? You try to project this data in some higher dimension. Which data? The data wherein classes are non-linearly separable. So these data set are projected onto higher dimension in such a way that I get a linear hyperplane in that direction, in that dimension. So to do this, I have to find a function to map that data into different space. So those functions could be called as kernel functions. These are just some of the mathematical equations which people have used to perform support vector machines. So I will not go into the details of these equations. These are very well known, published, so you people can refer to any of the reference. That's what I was telling in the beginning, that if there is non-linearity in the data, that means the classes are non-linearly separable. These are non-linearly separable in 2 dimension, so these can be projected in 3rd dimension, wherein this linear hyperplane can be obtained. But to do this, I have to use some kind of kernel function to bring that and into that dimension. So my kernel functions could be polynomial, Gaussian radial basis function, and a sigmoid function. Now again, just like neural network, there are various factors which we may take into account to really obtain quality information from support vector machines. These parameters could be penalty value, the multi-class method. As you all know, the classes are, so as I was telling you, that just like a neural network, there are a number of factors which may affect the quality of image classification when it comes to support vector machines. Say for example, setting up of appropriate penalty value, which we also call C value, the kind of multi-class method. Now as you know, support vector machines have been designed as a binary classifier, so I have to find out some multi-class strategy, what kind of optimizers are used, what are the kernel functions, and what are the hyperparameters which are used in those kernel functions. So my multi-class methods could be one against the rest, pairwise classification, even decision tree structure, and nowadays multi-class objective functions have also been designed. There could be different optimizers like quadratic programming, linear programming, chunking decomposition, or sequential minimization, minimal optimization, and even Lagrangian support vector machine. So having understood the philosophy or the logic behind neural network, spectral correlation mapper, and support vector machine classifier, let me now show you some results which we have obtained by applying these classifiers on a set of hyperspectral data set. This is again the same image, average image of Indian pine test site, which we have used for classification purpose and which contains 16 crop classes. So when I applied maximum likelihood classification, a parametric method, it basically failed in case of 16 classes, whereas neural network classifier gave me 38% accuracy and SVM gave me 97% accuracy, which in fact is a significant increase in accuracy of classification from hyperspectral data. Then I also used spectral correlation mapper and support vector machines to produce classification. I just want to focus you people here that this is indeed a minimum training sample size. Say for example only 9 pixel, and here 11 pixels of testing data set, and here also 9 pixel and 7 pixels. This is indeed a very less training sample size, and that was the reason that why maximum likelihood classifier failed. Now when I look at the spectral response of various classes, almost overlapping spectral response is there. So obviously the statistical classifier are not going to discriminate classes when such an overlap is there, and that is what happened in spectral correlation mapper classifier. You can see this is the kind of classified image which we obtained by applying a spectral correlation mapper with an accuracy of 34%, as you can see, and compare this with the equivalent difference map. But when we applied support vector machines, I could get an accuracy of 91%, and which is really very good so far as the classification from hyperspectral data is concerned. Then we also applied on a satellite based Hyperion image of Roorkee area and surroundings. So total number of bands were used 172 with an image size of 240 by 200 pixels, and there were 1, 2, 3, 4, 5, 6, 7 classes which were mapped. But as you can see here, unlike the previous data set, the classes seem to be separable. So when the classes are separable, then perhaps statistical classifier may be equally good, and that is what happened. This is the SCM or spectral correlation mapper classified image, which gave me an accuracy of 95%, and SVM further improved upon that accuracy, which came out to be 98%. So to conclude, that support vector machine classification appears to be the most appropriate classifier to produce high classification accuracy with minimum of training data set. Then we also did an experiment using decision tree classification. Just I will again explain a bit a concept of decision tree classification. It is again a non-parametric approach based on machine learning algorithm and uses divide and conquer strategy. It involves basically recursive partitioning of the feature space based on the training data set. So for example, there is a root node, and then there are other nodes, and then each node is divided into further parts till you get the terminal nodes where you will get the class labels. So it is in fact a three-step process, wherein the first step is the selection of a node splitting rule. So how to split the classes into two, and the decision as to which nodes are terminal nodes, and finally the assignment of each terminal node to a class label. When it comes to splitting rules, or attribute selection criteria, we have the option of Gini index, Turing rule, chi-square statistics, and information gain. And there are several decision tree induction or building algorithms which apply some of these rules, like CART, ID3, C4.5, and so on. This is just a remote sensing example that at first, say there's band 2, two values are there, it will be divided into 2 based upon certain splitting rule into C and then the next class, and here again the next data set will come, again you will divide that into 2 and so on till you get various classes. So here you are getting class 1, here you are getting class 2, and finally you are getting class 4, 5, 6, 7 and 9. So this is the way the decision tree classification works. So we applied this decision tree classification on the same hyperspectral image and we obtained accuracy of the order of 70 odd percent when we applied different splitting rules. So what I mean to say is that decision tree classifier can also be used to classify the hyperspectral images to obtain several classes from those image. Now till now what we have seen is that each pixel of that hyperspectral image is allocated to one class, and there are several classification strategies ranging from statistical classifier to machine learning classifiers. Now these classifiers are good enough so far as my pixel belong to one and only one class. But what happens when it comes to coarse spatial resolution? As you can see here, suppose this is the map which I want and this is the remote sensing data set which I have, for example say 80 meter data set. Then if I overlay this onto this image, many of the pixels appear to be mixed. So many of the pixels will be having more than one class. If that is the case, then per pixel, by applying per pixel classification, I am basically overestimating or the area of any class and underestimating the area of other class. So what should I do? I should go now for subpixel classification. So mixed pixel indeed is a problem. It is the mixed pixel may occur because of presence of small or subpixel targets, because of presence of boundaries of discrete parcels, or gradual transition between land cover classes. Why mixed pixels are problematic? These are because the spectral reflectance of a mixed pixel is generally the weighted average of the spectral response of the classes within it. Therefore, classifying mixed pixels using hard or per pixel classification may lead to error in classification. So as I told you earlier, the output from a subpixel classification is a set of class proportion images, what we call fraction images, equal to the number of classes. These images are also called as fuzzy outputs or soft outputs or probability outputs. Now subpixel classification also can be performed using parametric classifiers or non-parametric classifiers in supervised way or unsupervised way also. So this is what I just said, that I'll get a set of fraction images. Now for example here sand, so this is a sandy area indeed, so almost 100% is a sandy area, but these gray shades means that at this pixel level there is less sand and more of other class, and black means no sand and the pixel is dominated by other class. When I look at the subpixel classification algorithms, there are many. In fact, subpixel algorithms nowadays are used frequently for producing subpixel classification from hyperspectral data also. So for example, I have maximum likelihood classification in fuzzy form, linear mixture modeling. Fuzzy C means neural network. Even support vector machines can also be used to produce fuzzy classification, and decision tree classification, I would say decision tree regression can be used for soft classification. Just to start with, for example, my maximum likelihood classification can be used as a soft classification or subpixel classification strategy. In maximum likelihood classification, for example, I am finding out the probability of a pixel belonging to a class. When these probabilities are scaled from 0 to 1, then these probabilities, which we call posteriori probabilities, can be related to actual class proportions of the pixels on ground, and which has been proved. Similarly, in linear mixture model, there is a linear mixture model which exhibits a linear relation between the spectral response of mixed pixels and that of constituent classes weighted by their corresponding proportional area on the ground. So this is my observed data. This is the proportion which I want to find out. So it is a vector of class proportion, and M is the end member spectra. Now this is my observed data. This end member spectra is nothing but spectra of the classes which I want to map. This again may come from spectral libraries or from the training data. So this is a kind of linear equation subject to the constraints that my proportions over a pixel sum to 1 and that all the proportions are more than or equal to 0 for all the classes. So I can apply a least square adjustment process to solve this equation to find class proportions. As I said earlier, the M matrix, the end member spectra, can be obtained from the training data. So I need to identify pure pixels for a class from the image, and then average of those pure pixels can be taken as end member spectra, or these can be obtained from laboratory measurements. If the number of classes are equal to n plus 1, n is number of bands, then I get a unique solution. If number of classes are less than number of bands, then I get then I will use least square technique to get the solution. But when number of classes are more than number of bands, then I will not get any solution. Fortunately, in hyperspectral images, the number of bands are more than the number of classes, so this algorithm will work very well on hyperspectral data set for finding out the subpixel classification. So this is a unconstrained solution coming from least square adjustment, which is as you can see, this F is the class proportion, M is the end member matrix, this is the pooled variance covariance matrix. So the solution is M transpose sigma inverse M over inverse M transpose sigma inverse X. So this equation will give me class proportions of each pixel. Then there is another algorithm which I can use for producing subpixel classification, which is coming from fuzzy set theory. It is an unsupervised fuzzy C-means classification algorithm. Here again I am trying to find out these membership values via some optimization process by knowing the clusters in the image and the observed data. So it is a kind of distance function which I want basically to minimize. So it is an iterative process which will start with some random membership values mu ij and also the random values of cluster centers. So in an optimization process, the class membership values are obtained in this fashion to ultimately get the membership of classes in each pixel. Now these membership of classes can be related to class proportions within a pixel. I can also use neural network for producing subpixel classification. In earlier case, when I used neural network for per pixel classification, you might have noticed that at these pixel levels the values were 1, 0, 0, 0 and 0. So that was a per pixel classification, that means the pixel belonged to class 1. Now if I can really map those activation levels and scale those levels from 0 to 1, then those activation values will represent the class proportion. So just to summarize that I can use different outputs to represent subpixel classification outputs. For example, softening the hard classifier, that means for example maximum likelihood classification, so probability of occurrence can be used to reflect the class proportion. In fuzzy C means the membership values. In artificial neural network, the activation level. In linear mixture modeling, proportion or concentration of class. Even decision tree regression, the regression outputs. So I have applied linear mixture modeling model on that same hyperspectral image, and I started getting these kinds of fraction images for each class. So if you see now, class alpha alpha is represented here in this color, and that means this area should be having more of alpha alpha class here. So this has come as bright class here. So these kinds of gray shade images I can get for various classes. So this is for another class, this is for class con, this is for class again con min, and so on. So these fraction images will be generated from linear mixture modeling if applied on hyperspectral data set. So these fraction images will be equal to the number of classes which need to be mapped from that data set. Now what happens? Subpixel classification can give me information about the percentage of class within that pixel. It basically fails to account for the spatial distribution of those proportions within that pixel. In recent times, another technique which is in the offing is what is known as super resolution mapping, which considers spatial distribution of class proportions within and between pixels in order to produce maps at finer scale. So basically I am going to get fine spatial resolution data from coarse spatial resolution mapping. So here in super resolution mapping, basically two inputs are required. One, the spectral characteristics of the data. Second, the subpixel classification outputs. That means it has to follow subpixel classification. So this is what I just told you, that if suppose let us say I consider any pixel having more than 70% of a given class is considered as pure pixel. Here these are the 3 pure pixels, these are 2 pure pixels, but these let us consider these as 3 mixed pixels. Now when I apply class proportions, when I apply subpixel classification, so I will get 60% this, 40% this, 70 30, 65 35. But how these proportions are spatially located within the pixel is not obtained from subpixel classification, as you can see here. 0.6, 0.4. So these are the I don't know whether this is located like this or in any other way. So what I try to do here is that I would optimize these class proportions of a given class by gathering information from the neighboring pixels. For example, here if these are the two pixels which belong to this class, then obviously this set of pixels should belong to this class, so that means distribution should be in this way, and so on. So in an optimization process, I am going to find out the spatial boundaries of these class proportions within these pixels and ultimately get this kind of output through super resolution mapping steps. So there are several methods like pixel swapping method, inverse Euclidean distance method, and many more. So let us apply this on a data set. It is a data set which is freely available, which is a data set from every sensor at 4 meter resolution, San Diego area. So we utilize 189 bands, and you can see here these are some of the small aircrafts which are lying there, where the spectra is mixing with the background. So here we have applied a subpixel classification technique followed with a super resolution mapping method to ultimately get the targets. So we have taken a subset of those images. In addition to that, we have couple of synthetic data set. This is a kind of representing a circle, and this represent an aircraft. So these data were put through these super resolution mapping methods. Both the methods were able to give me outputs at different scale factors which resemble the original output on the synthetic data. But when it came to real remote sensing data, the pixel swapping method was not able to give me the outputs on both the images, but whereas the Euclidean distance method was able to give me the targets in this fashion. So in super resolution mapping, I can really get the spatial locations of the class within that pixel. So having said so, I can utilize whether per pixel, subpixel or super resolution mapping to obtain information from hyperspectral remote sensing data. Whether I am getting a classified image or a fraction image or a fine resolution image from hyperspectral coarse hyperspectral resolution data, those outputs need to be assessed for classification accuracy. Unless and until I attach a degree of quality to that map, it will not mean anything. So why assess accuracy? As you might have seen earlier also in earlier presentations, it helps me in analyzing the errors that may creep in during the classification process, whether it is per pixel or subpixel. It tells me how my tool performs. It allows me to compare results from two data sets, two interpreters and so on, but of course it increases my degree of confidence if I attach it. So to summarize, I would say that segmented PCA can be successfully used for reducing the dimensionality of hyperspectral data. A spectral correlation mapper, nonlinear support vector machines appear appropriate for hyperspectral image classification. Linear mixture model can be applied for subpixel classification from hyperspectral data. And finally, super resolution mapping is indeed an approach to generate fine resolution maps from coarse spatial resolution images. And since in hyperspectral imaging I am getting data at many different spatial resolutions, probably super resolution mapping would be the technique or the approach which one need to target in future. Thank you very much.